Well, welcome to EECS 151, lecture 23. We're getting near the end here. There's only a few lectures remaining, but we have some very important stuff to talk about today and for the last few. So thank you for being here. Today we're going to talk about latches and flip-flops, and then we're going to start talking about SRAMs, finally find out what makes those tick. But let's go ahead and start by refreshing on what we learned on Tuesday about timing analysis. So please go ahead and try this problem on your own. All right, let's talk about this one a little bit. I'm seeing a few puzzled faces. So let's recall a little bit from last lecture, okay? So on Tuesday, we talked about two key aspects of timing analysis and sequential logic. Setup time is concerned with slow paths. And in particular, you can think of setup time as the data and the clock racing to the capture flop at the next clock edge, and the data needs to get there first. If it doesn't, that's a setup time violation. Hold time is the data and the clock racing to the capture flop on that same clock edge that launched the data. And this time the clock needs to get there first. And so if the data is too fast, that's a hold time violation. At the end of last lecture, we talked about the fact that the clock, previously described as sort of this ideal signal that magically arrives at every flop at the same time, has these non-idealities, which we call skew and jitter. Skew is spatial variation. So the clock arriving at different flops at different times in the same cycle. And jitter is variation in time. So the clock arriving at a different, slightly different time each cycle. And so this warm-up is asking you to account for those non-idealities and understand how it impacts the setup and hold time of this path. So let's think through this. And let's try to just reason about it before writing any equations, right? So for setup time, the sign-off engineer has added this buffer. They've added 40 picoseconds of delay of positive skew to the receiving flop. So is that going to help or hurt our setup time constraint? Yeah, that's correct. Why? Right. Yeah, it's a race. It's a race between the data and the clock. The data needs to win, and we're delaying the clock. We're slowing it down, right? So in this case, this is sometimes called useful skew. So skew helps. And what about jitter? Right. Jitter always hurts because we always have to assume the worst case. Right. It might be forward one cycle, backward the next. It might be backward one cycle, forward the next. We don't know. So we always have to assume that it hurts. Okay. What about for holds? Does skew help or hurt hold here? Right. Yeah. And so you can see there's this trade-off where we're helping setup time, but we're hurting hold time in this case, right? And jitter always hurts. So now we can just use the numbers that were given to understand the impacts on the actual timing, right? So setup slack gets plus 40 picoseconds for the helpful skew, and then minus 20 picoseconds for the harmful jitter. So overall, the clock non-idealities are actually helping our setup time here, right? So the period is improved to 780 picoseconds. So we got a little bit of speed up, a little bit of frequency boost from that useful skew. We said hold hurts both ways, right? So minus 40 picoseconds, minus 20 picoseconds. And our hold slack at the start was just 50 picoseconds. So the updated slack is actually negative 10 picoseconds, which means what? What does it mean when the slack is negative? Yeah, it's a violation, right? It means that this circuit will fail, or at least have the possibility of failing, because it's violating the whole time constraint. So you'd have to go fix up this design in order to get it ready for production. Okay, any questions about jitter and skew and clock non-idealities? Yes, one question. Yeah, so unlike skew, which is deterministic, right? It's a non-ideality, but we can analyze whether it's going to be early or late. Jitter by nature varies from cycle to cycle, right? So it's you can think of it as like a Gaussian distribution of arrival times, if you like. And so in one cycle, it might help set up and hurt hold. And the next cycle, it might hurt setup and help hold. But you have to make sure the circuit works across all the cycles, which means that you analyze the worst case where it could hurt either one of them. Yeah. Okay, so this wraps up our discussion about timing analysis, which we went through on Tuesday. We talked about how sequential logic imposes these two key requirements for setup and hold time. Setup time is violated when paths are too slow. There are lots of ways to fix it, but in a pinch, you can always just reduce the frequency. So setup time is pretty much never going to kill your chip outright. Hold time violations result from paths that are too fast, and it is independent of frequency. And so if you have a hold time violation after you tape out, you're kind of in trouble. And then as we just saw, we talked about how clock non-idealities, while skew can be used intentionally and beneficially, in aggregate, they tend to make timing worse, and we have to analyze them carefully. Before we move on to the next topic, I do want to talk briefly about sort of a practitioner's perspective of timing analysis in practice. I know that you all have encountered at least some of this in your lab work and your final project work when you're looking at synthesis reports, analyzing critical paths, analyzing frequency, and so forth. But when you're taping out a chip, you need to be somewhat more rigorous about it than you've done in your coursework. So as we've mentioned, the key concept and the key difficulty with timing analysis is that you really need to check every single path in the design and make sure that it meets both the setup and hold constraints. And keep in mind that every flop will tend to have many paths going into it, right? So for a design with, say, 1 million flops, there might be tens or hundreds of millions of paths that need to be analyzed. You need everything to work. A single failure can break the chip, and it does. In practice, this is one reason that chips don't work. The process of guaranteeing that there are no failures is called timing sign-off. So you may hear that term in industry. And so the EDA companies have designed these tools called STA, static timing analysis tools, to perform sign-off as quickly as possible and as accurately as possible. It's called static timing analysis because it's not simulating particular vectors, right, and observing the toggles, but rather it's just considering the paths statically, right? The same way that we analyze delay by hand of combinational logic in previous lecture, it's doing that in an automated way with these very fast optimized algorithms so that it can look at every path in the design and sign off for setup and hold. And so these STA tools, you input the gate netlists. Yeah, one second. You input the timing constraints. If you want, you can tell it a layout, so it is aware of the layout-dependent effects, and it'll get more accurate results. And then it will output reports that analyze all the paths and tell you what the violations are, if any. And so you've seen similar reporting in your synthesis replacement route tools in the labs. It's doing sort of a quicker and less accurate version of these STA algorithms within the synthesis tool in order to produce that information. But the special software programs to do STA, Synopsys calls theirs prime time, Cadence calls theirs tempus. These are the things that engineers use to actually get a chip ready for production. And then you'll see these metrics in your timing reports. You have probably come across them already. You'll see reference to TNS and WNS. So now that we understand what slack is, we know that negative slack means there's a violation. So these terms are pretty easy to understand. So the worst negative slack is just the largest magnitude violation, the largest negative number of all the slack of the different paths in the design. The total negative slack is adding up all of the negative numbers. So every violating path, add up all the slack. So that can be helpful to see, is it really just one or a handful of paths that are violating, or is it many, many paths, and that's harder to fix? And then finally, I'll mention that we talked a lot about hold time in lecture, but you haven't focused on it that much in the labs, and that's by design. Typically, hold time is something that's fixed sort of near the end stages of the design after clock tree synthesis and the place and route flow. Because there's not that much point in trying to fix hold while the design is still sort of being optimized or tweaked by the earlier stages of the tools. So typically in the earlier stages, you just worry about setup time, and then near tape out and at the end stages of place and route, you focus on fixing hold. Okay, questions about anything I just said about the practitioner approach? Yeah.
Like you said, there's a timing sign-off. They use the static timing analysis tools for that.
That's correct, yeah.
Okay. They don't do it by hand.
Correct, yeah. No, none of this is tractable to do by hand just because of the magnitude of the problem. So they'll run these tools, and the makers of the tools have spent a great deal of engineering effort to convince you that if the tool says that the design is timing clean, then it's actually going to work properly.
Have total negative slack. Like that's a lot bigger than your worst negative slack. That means that you have like slack all over the place. So like, how would you go about like using that information to like optimize your design?
Yeah, good question. Typically you optimize the design by, kind of looking at the top N worst paths and looking where they are in the design and then trying to optimize or perhaps repipeline that part of the design. So if your total negative slack is not that big, it's just a handful of paths, then it's, you can just go fix that, or maybe even kind of fix it by hand in some cases. If the total negative slack is very, very large, then that's suggesting you kind of need to rethink. You may need to rethink your microarchitecture more fundamentally, or you may need to slow down your frequency target to have any hope of meeting it. Yeah. So this is getting a little bit into the weeds, but very late in the design process, when the design is mostly done, but there may still be a few bug fixes needed, engineers can do what's called an ECO, which is an engineering change order. And ECO you can just think of as kind of a late fix that's not rerunning the entire synthesis flow, but it's just making a tweak to one very specific part of a design that's guided by an engineer. So, the tool has to optimize 100,000 things, and if it misses 5 of them, it's not worth like going back to the start and rerunning your whole flow. Instead, you might just go in and ECO a particular path by, for example, you might move 2 flops physically closer together in order to ease the timing path between them, or you might upsize gates on that path deliberately. So that's a little window into timing sign off in practice in production silicon. I'm going to move on because we have some other exciting stuff to talk about today. We're going to start getting into latches and flip-flops. Okay, we've seen these. In particular, flip-flops we've been looking at since lecture 3 or so. But we're going to understand how you actually design them out of transistors now and how they work and why they're called flip-flops, which is kind of a weird name. But we're going to start with latches. which might seem like an odd choice because we haven't really used latches much in this class, but it turns out you need to understand latches in order to understand flip-flops. So we're going to start there. So recall that this is what a latch looks like functionally. This is the Verilog to generate it. If you've encountered a latch in your designs in this class, it was probably by mistake because we haven't really been doing latch-based design, which tends to be more complicated. But the key difference, as you may have learned by hard experience, is that instead of always at pause edge clock, we have always at clock. Right. And so if you think just sort of mechanically about what that means, that's saying we say if clock, then Q gets D, right? So a latch, as defined here, is transparent high. So when the clock is high, pass D through to Q. There's also an inverted version called a transparent low latch. When the clock is low, you pass D to Q. In the other case, for transparent high, if the clock is low, then we store the current value. So we would say that the latch is opaque in that case, the opposite of transparent. So you can see in the waveforms the behavior here. All right, it's a little bit like a flop, except that it's transparent all the way when the clock is high, not just at the edge, right? And you can see that, like we did for a flop, we can define these key timing constraints. All right, we have a setup time, which interestingly now is before the falling edge of the latch, because that's sort of when the latch closes, if you think about it. So the data needs to be stable before that falling edge. We have a hold time after the falling edge. We have a clock to Q delay, which is just the delay from the clock edge for D to propagate to Q, right? So it's this delay. And then we also have a D to Q delay. When we have these transitions while the latch is transparent, that means D is just going to flow through to Q immediately. So the timing constraints or the timing parameters look similar to a flop, but a little different. They're noted here for completeness. We're not going to really talk more about these timing constraints specifically today. Instead, we're going to talk about how to actually design the latch, how to build this thing. We're going to build it out of two components, both of which will look a little weird, but I think will yield to our analytical skills upon a little bit of deep thought. The first of these components is a cross-coupled inverter, which is shown here. It's literally just two inverters looped back on themselves. So this is kind of an odd structure. Why would you do this? Well, let's think about what the functionality is, right? So let's say this level here is 0. The VI1 is 0. Well, it gets inverted through that first inverter. So that's a 1. And then it gets inverted again through the second inverter. That's a 0. And then that is passed back to the input of that first inverter, which is still a 0. So the circuit doesn't really do anything in some sense, right? Just whatever value is sitting there at the start, that's what value stays there in the positive feedback for as long as it is powered, right? So on the one hand, it doesn't really do anything, right? There's no toggles, there's no transitions. But on the other hand, this is sort of exactly what we need for these stateful elements, these sequential elements, is that we need them to have memory. We need them to remember. And that's exactly what this circuit does. The circuit is a memory cell, effectively. It stores whatever value it has. Another way to think about or visualize the effectiveness of this storage cell is with these kind of overlapping transfer curves shown in the bottom left of the slide. So if you think back all the way to Oh, lecture 2, I think, is when we presented these. There's either 2 or 3 where we presented these voltage transfer characteristic curves. So this should look familiar. This is the transfer curve of an inverter, right? It's saying that when the input is a high voltage, the output is a low voltage. And when the input is a low voltage, the output is a high voltage, right? It's doing that inversion. And then we've taken that same inverter transfer curve and mirrored the axes in the second one, so that now the input is on the Y and the output is on the X, which again seems like a kind of a weird thing to do. But the reason we do it is so then we can overlay the plots as shown in the bottom part. And you can visualize the positive feedback, right? So for example, if the input here is kind of close to VDD, but maybe not all the way at VDD, well, that first inverter is going to restore the voltage to be very near to VDD, right? And then the second inverter is going to boost it up further until eventually it will be driven to this stable point. Or if you start somewhere in the top left of the plot, it'll be driven to this stable point. So this is just a way of visualizing the positive feedback of our cross-coupled inverter. So yeah, feels a little weird, I guess, or a little different, but nothing too mysterious here. Like we know how to build an inverter. We know how to therefore build 2 of them. So at least we understand what this is made of. We can see how it works. The second cell we need in order to build our latches is called a transmission gate. This is also going to look and feel a little weird compared to other kinds of cells that we've looked at so far in this class. Transmission gates are a way to build switches in CMOS, if you want to think of it that way. So let's think about the functionality here. We have A and then B, and then notice we have B bar, or the opposite of B, as the other input of the PMOS. And then we'll call the output Y, if you like. So let's think about the functionality. If B is 1, then is the NMOS on or off? If B is 1, the NMOS is on. And if B is 1, is the PMOS on or off? Careful. This is B bar, right? We're passing the opposite of B. So this is a 0 driving the PMOS. So is the PMOS on or off? Right, exactly. So when B is high, the NMOS and the PMOS are both on, which means that we're effectively shorting A to Y, right? We're connecting the source and the drain of both of these transistors, or we're shorting the source and the drain of both of these transistors by turning them on. And then conversely, you can see that when B is off, it's going to turn both of the transistors off. And so it's going to disconnect A and Y. So you can see that this is sort of the equivalent of a switch, right? Controlled by B. Conceptually. So let me ask you all a few questions, and then I'll take your questions. So one question is why do we need 2 transistors here? Right? It seems a little redundant, I guess. Because as long as one of them is on, it seems like it's going to connect A to Y, right? So why couldn't we just build the transmission gate like this? B, A, Y. Does anyone see the problem with this NMOS only transmission gate, which is also called a pass gate? Yeah. It is something to do with the pinch-off region, yes. Yes, start dredging up in your minds how transistors work. Okay, it's the same reason that we only put NMOS in the pull-down network of a CMOS gate, and we only put PMOS in the pull-up network of a CMOS gate. So what is that reason? Why is that? Recall that we talked about how NMOS are quote unquote good at pulling down, right? But if you try to pull up with an NMOS, you're going to wind up with a threshold drop across the transistor because it will pinch itself off before it can pull all the way up. So NMOS are good at pulling down, but bad at pulling up. Or another way of saying that is that NMOS are very good at passing zeros, but not so good at passing ones. So if we only had a pass gate, if A was 0, Y would be 0, no problem. But if A were 1, Y would never get to VDD. Y would, the closest it would get is VDD minus VT of the NMOS, which is typically several hundred millivolts off, right? That's very undesirable to have that much voltage drop in your switch. That's ostensibly just passing the input to the output. So in the transmission gate, we need the NMOS to pass the zeros strongly, and we need the PMOS to pass the ones. So we definitely need both of them. And this transmission gate is much more robust than the pass gate, but it still looks kind of weird. It looks very different than all of the other CMOS gates that we've looked at so far. So what are some key differences between this gate and, say, an inverter or a NAND gate? Yeah, what's one? Yeah, that's right. It's connecting the input directly to the output. And so in particular, the language I would use to describe that is that this is a non-restoring gate. Right? One of the things we really liked about CMOS so far is that every gate was restoring. Right? A signal would get to the input of the inverter, and then that's as far as that signal would go. The inverter would connect a clean VDD or clean grounds to the output. But here, this is not the case. We're not restoring the output from a clean VDD or clean ground. We're connecting the output directly to the input. And so this has a couple of effects, right? When this gate is on, it's connecting to the input, the output, which is what we want, but it also couples any input noise to the output directly, right? It's just tying them together, right? If there's noise on the input of an inverter, it's not going to have that much effect on the output because the output is being pulled cleanly from VDD or cleanly from ground. But if there's noise on A, it's going to couple directly to Y. And then the other consequence is what happens when this gate is off? What is the value of Y when this gate is off? Yeah, it's not being driven by anything, right? So the output is undriven. We also sometimes call it floating. Floating. In your RTL simulations, this would be represented as a Z state. So floating means that in practice, well, it'll keep the value it had for a while, but not forever, right? There's some capacitance on this node that can store the charge that was put there, but eventually it's going to leak away. So this is, again, is unlike the inverter. One of the things we really liked about CMOS inverters and complementary gates is that it was always either connected to ground or VDD on the output. It was never undriven. So this transmission gate is kind of breaking all our rules, right? And so I just want to emphasize that we need to be very careful about using this guy. We don't just want to lay it down willy-nilly in our circuits. We're going to be very judicious about using it. And in particular, it's almost always going to be preceded and followed by a buffer or an inverter to kind of limit the scope of the danger here because we're storing and we're not driving the output directly. Yeah, in particular, placing multiple transmission gates in a row in series is just is a very risky idea and is generally unwise. So this is our transmission gate. We'll see how to use it in a moment. But any questions about what makes it tick and what makes it a little different than other gates we've looked at? Yes. Say again. Good question. So if you add a buffer at the output immediately following Y, you can at least guarantee that the output Y is then going to immediately be restored going through that buffer to a clean VDD or clean ground. Right? It's not going to solve the problem, but you can contrast that with having multiple transmission gates in a row, where each one is just introducing more and more noise. Eventually, it might violate your thresholds that make the logic tick. Okay, so we've got our cross-coupled inverter. We've got our transmission gate. Let's go ahead and build a latch. This is a easy way to visualize a latch design. It's simply a mux in feedback. Right? Recall that what we want for the latch functionality is when clock is high, it passes through the previous value. Or I'm sorry, when clock is high, it passes D through to Q. And when clock is low, it remembers the previous value and outputs that as Q. And you can see that these latch designs, in particular the positive latch, does exactly what I described. Right? When clock is high, we select this input, this one input, the D input of the mux, and pass it through the Q. When clock is low, we select the 0 input and just feed it back on itself. And so the clock is the control signal that distinguishes between the transparent and opaque states. You can see what is drawn here expressed in Boolean logic. You'll notice that this Boolean equation is a little weird because Q appears both as an input and as an output. This is sort of what defines it as a sequential and not combinational element. It has memory because its output depends on its current state, on its value of Q. So here's how you build that mux-based design out of transistors. And in particular, you should notice a couple of elements that we discussed on the previous slides. Right? We have a couple of transmission gates here. That implements the mux. One of the transmission gates is on when clock is high, and one of the transmission gates is on when clock is low. So I think the easiest way to understand this latch circuit is to think about what happens in each of those states. So let's sketch it out. When clock is 0, Well, let's see. When clock is 0, that's going to turn on this top transmission gate, which is passing clock into the PMOS and clock bar into the NMOS, and it's going to turn off the bottom transmission gate. And so that makes our circuit look like this, right? We've got the inverter. This transmission gate is on, so it behaves just like a wire. Got the other inverter. They're in feedback. And then we have this other path, but this transmission gate is off. So that switch is open. And here's D and here's Q. So when clock is 0, let's think through the functionality, right? D is ignored. And this cross-coupled inverter is remembering whatever value it had previously and outputting it as Q. Let's look at the other case. When clock is 1, now that top transmission gate is off and the bottom one is on. So now D is no longer being ignored. It's being passed here directly and output to Q. And this switch is open. So that positive feedback, oops, I missed an inverter here, sorry. But the positive feedback between the cross-couple inverters is broken. So they're no longer remembering the previous value. Instead, it's just passing D through to Q. It's inverting it twice, so it's buffering it, which is fine. So let's summarize. Does this behave like a latch? Well, when clock is high, it's transparent. D goes to Q. When clock is low, it remembers whatever previous value it had. So I would argue, yes, this behaves exactly like the latch that we described in Verilog at the start of the section. So this is one classic way to design a latch cell. It looks pretty different than other kinds of complex gates that we've looked at so far, but I hope you can see that when you kind of decompose it into cross-coupled inverter and transmission gate, it's constructed of those two components that each of those are relatively straightforward to reason about. Okay, questions about this latch design? Yes. Right. So when clock equals to 1, let's see, that's the clock equals to 1. We are turning on the NMOS and clock bar is being put into the PMOS. So we're turning on this gate. Oops. We're turning on this gate and we're turning off this gate or this switch. Right. So this is closed and this is open. And so the only transmission path that's connected is D going through an inverter. So this is D bar, if you like, and then going through another inverter, and then it's going out to Q. Right. So the path is here. There's also a path into the other inverter but that feedback loop is broken, so it's not really doing anything. Okay, let's look at one more latch design. This one is, I think, a little more common in practice, but a little bit trickier to understand or even weirder compared to other kinds of gates that we've looked at. So this is a latch design that relies on state forcing in order to write into the positive feedback cell. So let's do the same analysis that we did on the previous slide to understand how this works. So when clock equals 0, well, we only have one transmission gate and it's off. Q, and D. So when clock equals 0, the input is kind of disconnected from anything important. And we have that positive feedback, those cross-coupled inverters that are remembering the previous state. So that looks good. So far, so good. What happens when clock equals 1? Well, now the transmission gate is on, the switch is closed. And so our topology looks like this. What's going on here? Let's think about a case where Q is 1. So this feedback node, or sorry, let's say Q is 0. This feedback node is 1, therefore, because it's inverted. And then let's say that D transitions from 0 to 1. Okay, so then this node is going to get inverted from 1, and so it's going to become 0. But wait a minute, this node is already being driven to 1 by this inverter, which is remembering the state from this 0. We haven't broken that feedback loop. So we have a fight at this node. This is called contention. This would show up as an X in your simulation in RTL. So that seems bad. What happens? How do we deal with this? Well, you'll notice that in a little bit of a cartoon style, this cross-coupled feedback inverter has been drawn very small. And so that's not a typo, that's deliberate. And what it means is that we size this inverter to be a much larger drive strength, right? We size this with NMOS and PMOS of width 4 or 8, and we size this at minimum size. So that means that this small inverter is going to have much higher resistance, much lower current to drive this output node than this much larger inverter. And eventually, the larger inverter will win the fight, right? It'll push the voltage low enough that eventually it'll flip this node to 0, and then it'll flip this node to 1. And then the feedback will pick up the new value. It'll overwrite the value that's being stored in that feedback path. So this latch design is a little risky, you could say, because it relies on this contention or this fight, and it relies not on the logic and topology, but just on the transistor sizing. It relies on this feedback inverter being able to be overpowered by the driver in order to write this cell. So this is very unlike any other CMOS gate that we've had some before, because it is not contention free. Which was another nice property of all of our CMOS logic. So you do still see this design style used sometimes. The advantage is that it saves you transistors, it saves you area. And flip-flops are so common that sometimes it's worth being a little more aggressive with the design. And as long as you're very careful and simulate it all different kinds of ways, you can convince yourself that it's going to work reliably. So this is another latch design based on state forcing. Yeah. Yeah, this is not a mistake design. This is not a example of a bad design. This is a real latch that is used in some production silicon. As we're going to see more when we talk about SRAMs, when you start to have these very common state elements that are repeated many millions of times in a design, it's worth being more aggressive or more deliberate and moving away from the abstraction of ones and zeros within the cell. Right? You can think of this state forcing is basically a resistive divider, right? Where it's this larger resistance of the small inverter means that voltage is not going to be at 0 or 1, but it's going to be at 0.2 or 0.1 or something. But as long as that's enough to exceed the input switching margin of the inverter in the feed forward path, then it will flip the state element and it will successfully write the value. Okay. Let's think about this kind of concept a little more. These are two latch designs that I've showed you. There are many more ways to build latches. We're only going to talk about these two today and one more, which I'm going to ask you to think about on your own. So please read this problem and then turn to a partner and talk about it. Okay, go ahead, look around, find someone sitting near you, and discuss. Go ahead and take 3 minutes here.
Yeah, I can imagine it working if you have a high clock speed and crappy old big processor. Yeah. I guess you maybe yeah. It's like the people from the problems who buy like 3,000 dollars. Yeah, but sometimes yeah. I guess this should be okay. Yeah. Yeah. So I guess in a simulation, I just feel this. But what is actually happening is figure out that it's going to be so go down one more level. I guess that is through the transition. So there's no current. So with the voltage, there's no current. What's happening? Why do you think I'm falling asleep right now? You got it.
Okay, my takeaway is everyone is very sleepy. Let's talk about this a little bit. Is this going to work? Who says yes, it's going to work? Who says no, it's not going to work? Some sideways are down. Why is it not going to work? For those that say no. Yeah. Okay, so what's the problem with that? Your voltage is going to leak away. Interesting. So if in the case where this latch is transparent, there's no problem, right? When the clock is high, D is connected directly to Q through two inverters. Right, we'll again think about it the same way. So when D is high, or when clock is high, it just looks like this. So That half, there's no problem that I can see. When clock is low, now we've broken the switch, right? So let's say that just before the switch opened up, D was 1, or D was 0, rather, and this intermediate node, D bar, was 1, and Q was 0. So now we've opened the switch. So what's going to happen to this 1, right? This is VDD. This is just charge. If we go down one level of abstraction, right? So there's some voltage which is charge sitting on the gate capacitance of that inverter. And it's just sitting there, right? There's no current path for it to flow away. So for a while, it seems like it should be okay, right? It's just charge sitting in a capacitor forever. But the problem, as was pointed out, is that this is not a perfect capacitor with no current path. There's leakage. There's leakage through the gate, and there's leakage backward through the transmission gate. So eventually, this charge sitting on this node will be in danger of leaking away. We can't guarantee that it won't. So yeah, I would be pretty nervous about using this in a modern design. Yeah. Oh, yeah, you're right. I've drawn it backwards. Thanks for pointing that out. Yeah, sorry about that. So this is actually an example of something called a dynamic latch. All of those CMOS gates that we've looked at so far have been static gates, which means that if you keep the inputs the same and supply power to them, they'll give the same outputs forever. Dynamic logic is a little different. It relies on nodes to maintain their state for some useful amount of time. Dynamic logic design styles actually used to be quite popular in the kind of 1980s and 1990s timeframe. Back then, leakage wasn't nearly as much of an issue, and people really wanted to make their designs faster and more area efficient because Moore's law was still, several orders of magnitude back along the curve. So there are actually many different styles of dynamic logic design that people used. This is an example of one, this style of latch. But in a modern process, this stuff really kind of went out the window in the 2000s or so. Leakage started to become much more severe. And today you wouldn't see a design like this used because it would be in danger of forgetting its value. Yeah. Yeah. So this node, even when undriven, there's two paths for the leakage, right? One is it can leak through the gates of the following inverter. We haven't talked about all these details of how leakage works in this class too much, but there is the possibility of leakage through the gate of a transistor. Typically, this is right. We try to make the gates the gate as small as possible to increase the capacitance, because recall that capacitance is inverse of the thickness between the two plates. And so in a modern process, the gate is very, very small, like think order of angstroms. And so there's actually a quantum tunneling effect where electrons in the cloud just occasionally whoop, jump between the gap. So there's gate leakage forward, and then there would also be leakage backwards between the source and the drain of the transmission gate, even if that transmission gate is off. That's probably the more substantial leakage path to worry about in this design. Okay, so we've looked at now three different designs of latches. Two of them are reasonably robust. This one is a dynamic latch, probably not safe to use in a modern process, unless you want to take a lot of risks or be very, very careful in how you use it. So we're gonna now, let's do administrivia, and then we'll talk about flip-flops. Briefly, project checkpoint 3 is due tomorrow, as I assume folks know. Hopefully that's on your radar. The checkpoint 2 checkoffs are looking pretty decent overall at this point. You do definitely still get late credit for things if you're not meeting the deadline. So please do try to get the assignments in, even if they're not ready right by the deadline. One last plug, please attend your lab sections. We've noticed a very strong correlation between people who are regularly attending their lab sections and people who have finished checkpoint 2. So if you're struggling and you're not going to lab section, this is an easy step that you can take to try and get back on track. Next item, homework 10 is due tomorrow. This is, I think everyone knows the drill by now. And then finally, next Tuesday, which is the 25th, we'll be having a guest lecture on formal verification. We'll be having a guest speaker from NVIDIA come and talk about that topic, which is not something that we're going to talk about elsewhere in the class. So I'd encourage folks to come and attend that. I think everyone will be pleasantly surprised when you find out who the guest lecturer is, but I'm not going to tell you right now. Yeah.
When would homework 11 be due, given that next week's Thanksgiving?
Yeah, so homework 11 is going to be due a week later, so 2 weeks from Friday, 2 weeks from tomorrow.
Okay.
And that'll be the last homework of the class. It'll be a little longer because it's covering 3 lectures worth of content instead of 2. Yeah. That'll be released tomorrow, but it won't be due until 2 weeks later. Okay. Oh, sorry. One more question. All right. So let's move on and talk about flip-flops. Now that we understand latches, it turns out are the really tricky thing to wrap your head around. Once you get latches, flip-flops are actually pretty easy. Here are 2 different ways to design flip-flops. The one on the right is called a pulse-triggered latch. The key trick with a pulse-triggered latch is that you take your normal clock, which has a 50% duty cycle, so equal amount of time spent rise, high and low, and you somehow transform it into a pulse where it's only high for a very short amount of time, and then it's low for the rest of the cycle. So this is what the kind of pulse-based clock might look like. And then you can use that to drive a standard latch. Remember, the behavior we want from the flip-flop is that on the positive edge, the rising edge of the clock, it passes data from D to Q, and otherwise it remembers the value. So hopefully you can see how the pulse-triggered latch pretty much does exactly that, right? Because it's only going to pass the value when the clock is high, which is just for this tiny pulse. It's almost like passing the value just at the clock edge. So one way to build a flip-flop is with this pulse-triggered latch. This is not that common. We're not going to talk more about it today. The standard way to build a flip-flop is shown on the left, which is just a pair of latches, two latches. Okay, we typically refer to the first one as the primary latch. The second one is the secondary latch. You'll notice that this first one has a little circle on the clock, so this is transparent low. The second one is transparent high. And we just put them back to back like this. So how does this make a flip-flop? Well, let's try to understand that now. Okay, this is our latch pair. I've built it out of two of the mux-based latches that we saw previously. But the so it's a fair amount of transistors and all, but hopefully you can see the building blocks pretty easily, right? Here's the primary latch. And here's the secondary latch. Someone at some point 50 years ago thought it would be cute to call it a flip-flop because the first latch flips and the other one flops. I don't know why, but that's where the name comes from. You'll also notice that there's an extra inverter here because recall that we need to get clock and clock bar in order to drive the latches, the transmission gates. So the clock inversion is typically done inside the flip-flop cell. And another option would be to distribute a clock and a clock bar everywhere throughout your whole chip, but that's pretty expensive. And so it's typically cheaper and cleaner to just distribute a clock everywhere and then locally derive clock bar. So how does this thing work? Well, we have these two latches and they're basically going to be taking the data in and then handing it off to the next one. Let's step through it in detail, okay? Let's first think about the behavior of each of the latches during the positive and negative phases of the clock. So when the clock is high, well, the primary latch is transparent low, right? So when the clock is high, the primary latch is going to be opaque, which means it's going to hold its current value. And then when the clock is low, right, it's going to be out to the clock edges. When the clock is low, that primary latch is going to be transparent. And it's just alternating back and forth, which this means it's passing the data through. So that primary latch is pass, hold, pass, hold. The secondary latch is doing the opposite, right? So when the secondary latch, the clock is high, it's going to pass the data. And then when the clock is low, it's going to hold the data. Pass, hold, pass, hold. So how does this make a flip-flop? How does this combine to make the behavior of a flip-flop? Let's go through this example and understand it. Okay, I've notated this intermediate node as QM. So notice that D has transitioned here after the clock edge, but during the high phase of the clock. Well, let's think about what's the behavior of that primary latch during this phase. It's hold, it's opaque. So the input has no impact on QM, right? Because that latch is just remembering its previous state. Okay, now there's another transition of D, but now that first latch is transparent. So we're during the low phase of the clock, right? This transition is going to cause QM, that intermediate storage node, to go low. And then there's no more transitions here. What's going on with Q? Well, Q is the output of the secondary latch, right? When the clock is high, that secondary latch is passing through the value of QM. So it's passing the high value. Now, after the clock edge falls, that secondary latch turns opaque. It's holding the value. So that means it's ignoring any transitions that happen until we get to the next clock edge, right? Because at that clock edge, now suddenly that secondary latch transitions to a pass-through state, a transparent state, which means, okay, now it's going to pass QM through to Q. And so that means as a response to this clock edge, it's going to update the output. So do you see how this is exactly the flip-flop behavior that we wanted? On the positive edge of the clock, update the value of D to go to Q. Otherwise, just keep Q as is. Right? The primary latch kind of sets up the value, or sets up capturing the value of D and stores it at that internal node QM. And then the secondary latch at the rising clock edge passes it through. So this is the timing behavior of building a flip-flop out of two latches, primary and secondary. Questions?
And voting print on directly eyes, one goes down. Basically, like what it is to give it.
Right. So QM is driven only by the primary latch. And so it's either going to take the value of D if that latch is transparent, or it's going to just remember its previous value if that latch is opaque. Yeah. And then similarly, Q only depends on the value of QM. Same thing. It's going to take QM if the latch is transparent, and it's going to remember its previous value if that latch is opaque. And so by having this sort of staggered two-phase approach, you kind of set up the transition when the clock is high, or you set up the transition when the clock is low, and then at the edge, when the clock goes high, you pass that transition out of the secondary latch. Yeah, so it takes a little bit to wrap your head around this behavior, but I'd encourage folks to look offline, think about some other transition patterns for D and how they would propagate through to Q, not until the following rising clock edge, right? Because that's kind of the key behavior that we want for our flip-flop. Okay, let's do a little break. I guess we're almost at the end here. So we'll do a quick break and then we'll talk just for a few minutes about SRAM and then we'll wrap up for today. But I'm curious where people are heading next week. I guess I could also respond to this. Let's see if I can figure out how to do that. Or 111. Oh, I hope not. Take a break. Okay, looks like the distance winner is Maryland currently. Is anyone going farther than that?
Where do you go?
I will be going to Denver, Colorado to visit my parents.
Is that where you go?
It is not. They moved there like 10 years ago. So I had not been there really until they moved there. Okay, well, I encourage you, those maybe someone will like bring a Thanksgiving meal to outside Corey 111 or something. You guys can have a nice meal together before you get back to debugging. All right. I know we only have a few minutes left. I'm gonna just motivate SRAM as a teaser for our coming lecture after the Thanksgiving holiday. We'll get into more detail about it. So briefly summarize what we talked about so far today. We know that latches retain their state when they're not transparent, and we build them using these weird non-restoring transmission gates as well as cross-coupled inverters. We typically build a flip-flop out of a latch pair. Okay, so here's our SRAM teaser for today. We're just going to motivate why we might want SRAM. Those of you in ASIC lab have definitely encountered these so far. In FPGA lab, you've been using the BRAMs, block RAMs, which they're built out of SRAMs inside the FPGA. So you've actually been using SRAMs as well. As you know, in your processor designs, even these small processors that you're building, you need to store a lot of state, right? So what's the size of your typical memories, like the instruction memory in your processor, for example? Is it, I don't know the answer. I'm asking you all. Is it like 16K or 32K or how big is it? Or bigger? It's going to be probably in the kilobytes somewhere. And that's for your little tiny processor design. For a much bigger chip, you're going to need even more SRAM. Right? A real processor would not just have an L1 cache measured in the tens of kilobytes or hundreds of kilobytes, but it'll have multiple levels of cache. The L3 cache, last level cache, can be in the tens or hundreds of megabytes for a big Intel many-core CPU. Similar for GPUs, we have these big register files in the SMs. So you wind up needing to store many, many millions of these bits on chip, right? For whatever application you're talking about. So one option is to just draw it in Verilog like I've done here, right? So this is my memory module. I just have a 2 to the 20-bit register, right? And I say, okay, well, if write enable, write to it, and then otherwise read from it for the whatever address we pick. This is valid Verilog. It's not going to get you very far if you try to actually build this thing. One thing you could think about optimizing is that we often, for example, in your instruction cache or instruction memory, you don't actually need to access one bit at a time, right? You typically need to access a whole instruction, 32 bits at a time. So we can grab a whole word. We don't need to address all the bits individually. But nonetheless, if you tried to build this with a sea of flip-flops, millions and millions of flip-flops, it's not going to work very well. Your design is going to be 99% flip-flops by area. It's going to be really hard to route. The tools won't like it. So SRAM is an attempt to do better than just a sea of flip-flops for when we need very high capacity storage. Okay, and I'll just flash this slide and we'll conclude for today. So an SRAM consists of an array of bit cells that are very highly optimized in area in order to squeeze much more storage into a given space on your chip. Okay, and so after the Thanksgiving break, we will talk more about how SRAMs work and how to build them and how they're typically used in modern ASIC design. All right, that's it for today. Thanks, everyone.